Let's try to solve this problem here. So you have an object which is located 14 cm in front of a convex mirror. So if it's a convex mirror, okay, let's extract the information slowly. Okay, so located 14 cm in front. So if it's 14 cm in front, it tells you that this is the object's position, right? So object's position means by this is u, and u will be equal to 0.140 meter. Okay, for u, I think we can almost safely assume that the u, the object distance, will be a positive value because the object will be on the same side as the incident ray. Most of the time, 99% of the time, okay, unless it involves more than one lenses, which is that one will be in later sections. For mirror, if it's one single mirror, one single object, it's standard that the u will be a positive value. Okay, so because the object is on the same side as the incident ray. Okay, so this is a convex mirror, so a convex mirror. So if it's a convex mirror, you should expect the mirror to look something like this. Okay, so if the mirror looks something like this, then here will be where your incident ray will be. Okay, this is your update axis. So reflected will also be on this side as well. Incident reflected will both be on this side. Okay, but our center of curvature is somewhere around here in order to form a circle. Somewhere around here. So your center is on the right. Your center is on the right hand side of the vertex, while your reflected ray is on the left hand side of the vertex. So your reflected left, your center of curvature right, they are on opposite side. You should expect that the R is negative and the F will be negative as well. Both of these will be negative. Okay, continue. With the image being 7 cm behind the mirror. 7 cm behind. Okay, we know that this is the object where the image will form, sorry. Okay, image being 7 cm behind the mirror. This is where the image will be formed. So this will be image distance V, and it's 7 cm, so it's 0.070 meter. But again, we have this kind of value. We have to make sure whether it's positive or negative. So they say that it's 7 cm behind. 7 cm behind is the opposite of front, right? So if front is on the left hand side, so behind will be on the right hand side lah. So that means by if you pull from your vertex, your focal point, your image will be somewhere 7 cm over here. Okay, this will be your image. Okay, so we can almost safely assume that this image should be virtual, and at the same time V will be negative. Why is it virtual and why is V negative? It's because it's behind the mirror. So if this is the mirror, your image is on the right hand side, image is behind the mirror, but reflected ray is in front of the mirror. So your reflected ray and your image will be on opposite side of the spherical mirror. Okay, again, virtual image here is on the right hand side of the vertex, whereas the reflected ray is on the left hand side of the vertex. They are on opposite side, so you should expect that their image distance to be negative because the image and the reflected ray are in opposite side of the mirror. So V here be a negative value. Okay, so this is for the first sentence only. Okay, besides that, right, we should also know that convex mirror, right, because this is convex mirror, it always output one kind of characteristics, which is virtual, upright, and diminish. This is the quality that you should have if you are talking about a convex mirror. Okay, so because it's virtual, you should expect that V is negative. Because it's upright, you should expect that the magnification or the height of the image to be positive, and should expect that diminish means by your modulus of m, your m without looking at the sign must be less than 1. Okay, so you have to achieve these three requirements in order to be an image that is formed by the convex mirror. Okay, a second object twice as tall as the first one. Second object twice as tall. So if it's twice as tall, we know that the new object, which is HO, height of object for 2, will be equals to, as the first one, okay, it's twice as tall as the first one, so it will be 2 times of the height object of 1. Okay, so this is what we know for 1. Is placed in front of the mirror but at a different location. So for U1, we have to label clearly this is U1 because this is only available for the first situation. The U2 will be at a different location maybe. Okay, which is the second scenario. The object will be placed at a different location. Okay, the image of this second object has the same height as the other image. So the image should be the same height. Same height as other image. Okay, image same height as other image, so it means by H image of 2 will be equals to H image of 1. Okay, because we say that the image have the same height as the other image. Okay, so how far in front of the mirror should the second object be placed? So they want the object be placed at where? So this is U. What's the second object? So this is U2. They are trying to ask for U2. Okay, so let's try to determine what do we have for now. Okay, what we have for now is you have U, U1, and you have V1, right? Okay, for the first situation, the first scenario, you know the position of the object, you know the position of the image, then you can easily determine the focal length from here. So what can we do now is to use the object distance U1 and the image distance V1 over here to determine the focal length of the mirror first. So it's a simple mirror equation that we'll be using right now. So A is equals to U1 plus 1 over U1 plus 1 over V1 is equals to 1 over F. We need to label it as U1 and V1 because this is based on the first scenario. But F here, we still leave it as F because this same mirror here will be used for the second scenario. We are not changing a mirror, so there's no need to differentiate between F1 and F2 over here. So you substitute U1 to be positive 0.140. V1 over here will be negative 0.070. So from here, you can get your focal length. If you calculate it, your focal length will be equals to negative 0.140 meter. So does this make sense or not? Yes, it's because you see that F here is negative, and we already predicted that because it's a convex mirror, F should be negative. So the answer still makes sense, so we can move on to the next part. Okay, we're interested in how far in front of the mirror is the second object located. So second object means by we're interested in U2, right? So we might need to use the focal length that we determined right now to find U2. So this will involve using mirror equation again, but this time is for the second scenario. So it's U2, 1 over U2 plus 1 over V2 is equals to 1 over F. Okay, the thing is we have the focal length, that's correct. Okay, but the problem is we don't have both the object distance and the image distance. We don't have both of it because it's based on the second scenario, which they don't give a lot of information about. But we can actually try to determine the relationship between U and V over here because we know something about the height for the second scenario. We know that with respect to the first scenario, the object the second object is twice as tall. With respect to the first scenario, the image of the second image is the same height as the first image. Okay, so those relationship here we can use those relationship in the question over here regarding the height to determine the relationship between the U2 and V2 over here. Okay, so we know that magnification is equals to negative V over U. At the same time, magnification is also equals to HI over HO. So the first scenario, for the first scenario, which is M1, we can determine the magnification through negative V1 over U1. This is for the first scenario. We have the V1 is negative 0.070. We have U1 is positive 0.140. So from here you can find that M1 is equals to positive half. So this is the magnification of the first scenario, but the magnification changes because you place the object at different position, and at the same time it's a different object that we are talking about. So we change the object, we change the object distance, so all this changes the magnification as well. So we cannot just say M1 is equals M2, we have to figure out a new magnification for M2. But we know that M2 over here, we have some relationship that we can try to determine. Okay, M2 here is equals to negative V2 over U2, but at the same time, M2 is also equals to HI2 divided by HO2. We are going to exploit this relationship here because you know HI2 is equals to HI1, HO2 is equals to 2HO1. So we are going to use this relationship over here. So because M2 is equals to HI2 divided by HO2, we can equate it to HI1 using this relationship that we extract from the problem. HO2 will be 2HO1. So we replace HO2 with 2HO1. So right now, what do we have here? What I have here over here is HI1 divided by HO1. HI1 divided by HO1 is actually just M1. So actually, we can replace this HI1 over HO1 here with M1. So M1 divided by 2 will get you M2. And since we know that M2 is positive half, so this is positive half divided by 2. You know that M2 is positive 1 over 4. Okay, knowing this M2 is important because if you relate it with M2 is equals to negative VV2 over U2, you can say that M2 is positive 1 over 4 is equals to negative V2 over U2. So V2 is equals to negative U2 over 4. Okay, so now through this relationship between M1 and M2, over here, relationship between M1 and M2, we are able to figure out a relationship between V2 and U2. And this is very important because we can use this relationship between V2 and U2 to figure out V and also to figure out U. Okay. Okay, so U2, I'm going to retain it as U2, no problem with it. But for V2 over here, I'm going to replace it with negative U2 over 4. So plus V2 over here, replace with negative U2 over 4. Then the focal length here will be negative 0.140. So since right now the only unknown you have is U2, we can easily put this into a calculator to determine U2. And U2 is equals to positive 0.420. Okay, so it's a relatively long question, I think, compared to the other question. This one is not so direct, but you can see that every time we want to relate between U and V, we have two ways of relating it. One way is by relating it with the focal length, so 1 over U1 plus 1 over U1 is equals to 1 over F. Okay, so this is one way of relating U and V. Another way of relating between U and V is through magnification, because magnification is negative V over U. Okay, so there's two ways to find the relationship between V and U. So if you use them together, it's usually just a simultaneous kind of relationship. You use one way to determine the relationship between V and U, then you input the relationship into another equation to determine either U or either V. Okay, it's quite a typical way of solving questions. If you have not much information, try to use both equations to determine the relationship between V and U to solve for V or to solve for U. Okay, so that's it for this question. Thank you very much.